More than any other kind of long-distance communications, HF requires the user to select a very specific frequency for a particular time of day, and a given distance, in order to reach the receiver. The science and statistical modeling involved in predicting these frequencies are understandably very complex. Regrettably though, most frequency prediction applications tend to reflect this complexity, which many users find quite intimidating. The South African National Space Agency has developed a new application which offers a superior operational solution for high-frequency communication. It is called IOCAP. It comes in the form of a modern, user-friendly HF frequency prediction application that is easy to learn, and effortlessly produces superior prediction results. With its comprehensive set of tools you will create frequency predictions with the minimum amount of fuss, and, importantly, without having to work through multiple pages of cryptic numbers trying to find the detail you need. The primary work surface is a dynamic map covering the entire globe, enabling you to zoom in to street level at any geographic position. There is also a complete second map providing alternate detail, which includes the use of a satellite map. IOCAP allows you to create three types of predictions. The first is a conventional point-to-point prediction where a simple radio circuit from station A to station B is predicted. The assumption here is that station A is functionally identical to station B, and therefore the outbound and inbound circuits are also assumed to be the same. Unfortunately, this is seldom the case in real life, and asymmetric circuits are in fact the norm, rather than the exception. For this, IOCAP has the solution. It is called a reciprocal prediction, and is used in these cases where the two stations in the circuit have significantly different endpoints. For a reciprocal prediction, IOCAP creates a pair of predictions. One from station A to station B, using their unique specifications, and then a second one from station B back to A, but this time using station B's transmitter and A's receiver. The two predictions with their respective predicted performances are then laid next to each other for easy comparison. Note that this feature differs significantly from simply reversing the circuit direction, as one sometimes finds as an option in prediction software. The third type is called a roaming prediction. In this mode we have a stationary base station, and a constantly moving receiver, such as a vehicle or ship. An infinite number of waypoints are then specified along the route, and IOCAP predicts either a point-to-point, or a reciprocal prediction, between the base station and each waypoint. Prediction results are shown in tables with color-coded columns to enhance readability. Any value shown in green indicates an acceptable number, while red means there is potentially a problem with this value. So, even a cursory glance will provide a first-order indication of the quality of communications we can expect. During the prediction run, the predicted frequencies are compared to the list of frequencies that are available to the user. A separate, color-coded column is then shown with these closest matches. Time-consuming manual comparisons between predicted and available frequencies are a thing of the past. Instead, IOCAP provides easy-to-read, yet comprehensive and visually attractive charts and tables to display the predicted performance of the matched frequencies. Results can be exported for further analysis to the built-in spreadsheet, or converted to a variety of document formats to facilitate easy document sharing. They can also be emailed as attachments directly from IOCAP. At Sansa we understand that today's HF users require much more than just a list of predicted frequencies to fulfill their operational needs. Therefore, IOCAP offers a carefully selected suite of web-based data displays. To stay abreast of what's happening in the planetary geomagnetic environment, a real-time chart is available with a 3-day geomagnetic forecast. This allows you to adjust your predictions according to the prevailing geomagnetic conditions, making them more accurate and reliable during periods of unsettled solar activity. You can view historic sunspot data that goes back 250 years all the way to 1770. This time period can be dynamically filtered to view any specific time span and makes a great training aid, besides being useful for a better understanding of the all-important solar cycle. Solar cycle behavior can be studied in further detail with data going back as far as 1755 and covers all 24 solar cycles to date. Because HF transmissions are dependent on the condition of the ionosphere, which in turn depends on the radiation it receives from the Sun, it matters to HF operators whether either station in the circuit is situated in daylight or in darkness. With this real-time twilight zone map, no calculations of time zones are necessary. The HF user can now make informed decisions to establish intelligible communications at all times during the 24 hours in the day. To assist users, IOCAP features a comprehensive help system. Context-sensitive help screens are available throughout the application at the click of a button. A series of screen simulation videos is also available to train new users in the operational use of the application, as well as to refresh existing users when they have not used a particular function set for a while. In this brief introduction, we tried to give you a glimpse of how IOCAP breaks new ground in creating easy-to-understand HF frequency predictions. It brings together space weather, science, and practical HF expertise in one software application in a fresh and innovative manner. In the process, it deliberately parts ways with the convention that frequency predictions should be difficult, simply because the science they are based on is demanding and complex. At Sansa, we believe IOCAP shows that it doesn't have to be that way. And this is why we think HF just got a whole lot better.